I'm Anshuman. I'm a final year PhD at the Max Planck Institute for Astrophysics, and today I'll be talking to you about machine learning on simulations and for simulations. Let's see how much of it we do. And in a previous discussion session, it came up that there was not much about high redshift. Today, I think briefly in Chris's talk, we saw a mention finally of the epoch of reionization. But anyway, let's start off. So what is the epoch of reionization and why am I so interested about it? Well, we have this cool schematic that we really love to show you. If you go to any reionization talk, you'll see this guy. And what we'd like to point out is that while we have observations of the CMB, we have observations at present day. The amount of observations, of course, is building, but is still fairly lacking in this period, where essentially what we had was the first of pretty much everything that you're interested in. The first stars, the first galaxies, black holes, you name it, formed. And in various different processes, what they did was they release photons, which would ionize the atomic hydrogen around them. And why is that important? Well, we need to understand how exactly did this process happen, because the timeline, rate, and the processes of this reionization process progressing gives us an idea about the formation of all the different astrophysical objects that formed during this period and that we see today. And there are many ways we can study this, but the one that I will be talking about is the IGM 21-centimeter signal. And again, there has not been an introduction for this, so let's go ahead. So the 21-centimeter signal essentially is a forbidden transition from the parallel moments of the proton and the electron of the hydrogen atom to being antiparallel. And usually what happens if you have a box of hydrogen, I don't know if you have that lying around, but if you have that, you would not see photons. You would see them just colliding with each other, switching between these two configurations, but not much of photons. But what we believe about the IGM during this period is that it had two really important factors. One, that it was really less dense. You had gas clouds of very low density, so the atoms were too far apart to collide much. And secondly, we had lots of hydrogen everywhere. Like pretty much anything that was there in the universe was hydrogen. And thus we believe that we had this unique situation in the IGM. We had low densities, lots of hydrogen, so we should be detecting 20-centimeter photons from this period. So where are we currently? Well, it is not so fun, but here we are. If we look at the power spectra at large scales, about 10 megaparsec over H for the 20-centimeter signal across redshift, we have different simulations shown in blue, like this dashed one, dotted one, and that weird one there. And we have a bunch of observational upper limits shown as dots. What we see is that these are upper limits, and they are at best, if we take a look at these values here, an order of magnitude off from our signal. And this is mostly because we are dealing with situations with massive foregrounds and noise. Noise is easy to deal with. We just observe for longer hours, 1,000 hours here. SKA, whenever it's built, we want to look at the sky for 1,000 hours with it. Sure, great. But the main issue is foregrounds. And there are two ways people deal with it. And it's obvious why it is a problem. It's because we are looking at things which are so far away, so we need to peer through a lot of things. And one way is just to avoid wherever the regimes where they dominate. The other is to identify the foreground and remove it. And the LOFA team tries to do this removal process. And today, earlier in a talk, the Gaussian processes were introduced by, I think, by Max. And that's essentially what we use. We basically assign different functions for each of our components. One is the foreground, one is the systematic axis, one is the 20-centimeter signal, and each of them is represented with the Gaussian process, mainly identified by its covariance matrix. But the problem that we deal with is that we do not really know what the 20-centimeter signal would look like. So any covariance matrix that is assumed is always an assumption, and we might fit the data, we might get results, we might publish papers, but the astrophysics you get out of it could be wrong, could be completely missing the marks. And thus what we decided to do is where we finally come to the topic of this talk, and that is firstly machine learning on simulations. We used a variational autoencoder-based algorithm to train on the Grizzly simulations, where we take n-body simulations, make certain assumptions about baryonic physics with a very simplified model, and then do radiative transfer as a post-processing step. We tested this with like a variety of mock signals from pretty much every kind of code that exists for simulating the signal, from semi-analytic codes to full hydrodynamic codes, and we showed that the machine learning kernel does better. And then we wanted to test it with real data. The key thing we wanted to do was to see if we just replace an analytic kernel with a machine learning kernel and replicate the entire process, forgetting about everything else, then what do we get? One of the key things in past results was that they could not separate the excess noise, systematic excess, and the signal to be different because they were highly correlated in terms of their parameters that they recovered, so they reported them jointly. They're like, we can't do any better, we just do it like that. So we also do it like that. We take machine learning, we do the exact same thing, we get pretty similar results. But what we see is that our parameters are actually not correlated. Something that we are getting is not really that is something that's completely lost in the systematic excess. So we try to separate them out, and this is what we see. As expected, the excess noise is a dominant component. That's why it was dominating earlier. But now we are getting a really deeper upper limit. Of course, does not seem like much, but it's still almost an order of magnitude difference. And we are able to get this simply by taking the existing architecture and just replacing a covariance matrix in that. But of course, we don't really know what's the source of the excess, so we can't really say much again. But what we do see is that if we really look at the contours, we see that the parameters that we get for the Tonnesen center signal and pretty much everything else is uncorrelated. So even if our machine learning kernel is not picking out on the entirety of the Tonnesen center signal, whatever it is picking out is different from everything else in the data, which is already a pretty cool thing based on as compared to what we have done in the past. So what's next is to basically identify what is the systematic excess, why does it exist? We do not expect it to be there, what's it's doing. We want more data. That is, again, it came in one of the discussions. We want more data. We want to go to higher redshifts. We want to go to lower redshifts and do everything again. And the next part, which is very interesting, is to do everything with much better training sets. And there was a discussion about using phased flip simulations. And we showed in the past with various simulations, like from semi-analytic codes to hydrodynamical codes, that the fixed and paired initial conditions help to improve Tonnesen signal statistics. And we also want to vary cosmologies, astrophysics, to basically have more amount of values in our training sets. And this is where, if you would notice something at the corner, that guy comes into play, the polar simulations. Yes, if you would have noticed, yeah, we are going on a very bears-related theme. The first radiative transfer code was called bears. Then it evolved into grizzly, and now we have polar. What polar essentially is just an n-body code. For first test, I just ran what I call a small box, which, to give you context, something that is called a manageable size box is around 500 MPC over H for these simulations, because our power spectra are most sensitive at large scales. And then instead of just doing something simplified, we use semi-analytic modeling with L galaxies to factor in galaxy evolution, and then we do radiative transfer with Grizzly. So the key question that comes up is that now we are introducing more parameters. We want to vary more things. Does it really matter? Does it really give us a training set which would be of a parameter space that we would want to explore? And that's the question we ask. And the answer was interesting. Before going to the answer, sorry. We look at like a few example cases. So I chose 4 different models. One was we called fiducial, which was just Planck cosmology. The H high just took supernova values. Sigma 8 low took BOSS measurements. And Sigma 8 high used E rho zeta measurements that came earlier this year. And we could vary a lot of astrophysics, but we chose to just focus on a few which seemed to have a big impact, because the idea was not to get everything right, but to just show that different parameters can be varied to give us some very similar looking results. So in particular, we focused on the star formation efficiency controls and the energy release per supernova. And we first looked at what you would see with JWST by looking at the UV luminosity functions. The target was redshifts 9 and 10, but the interesting thing was that we pretty much replicate this plots from anything ranging from redshift 5 to redshift 14, getting the brightest galaxies as well that have been so far seen. And what we see is that all of these models pretty much replicate it, because that's how we set the astrophysical parameters. And if we look at how the Tonnesen signal would look like, the fiducial one is something like this. The H high, something very similar. Sigma 8 high, again very similar, and even sigma 8 low is very similar. We don't see this bump because, again, I took a simplified model. I did not put an X-ray heating, so we don't get this guy here. But what we essentially get is that even with very different cosmologies and astrophysical parameters, we get all of these values, which, sure, they have some differences, but they are all in agreement with whatever upper limits we have. And they are fairly similar, despite having, like, if you look at, say, for example, images of of slices or something, we see very different ways in which reionization progresses in these boxes. So taking all of those into account is important, because we are otherwise losing out on perfectly viable models which would agree with pretty much all observations, but are just ignored because we just did not run them in the past, which is what the LOFA team was earlier doing by assuming certain cosmologies, certain baryon properties, and just going ahead with it. There are ways to, then you would say that, okay, now we have so many viable models. What do we do with so many models? We want one model to explain us what exactly is happening in the universe. So then we look at other observables. One way is maybe to track neutral hydrogen fraction and how it evolves. Of course, you could look at the end of reionization with Lyman alpha forest observations, but it's still a bit noisy. We see an entire spread here, and pretty much all of them kind of seem like an agreement. But it's giving us an idea about what all we could use. And that is the goal that I want to proceed with, and that is to expand the parameter space of models to see all that are viable, and then do this basically multi-observation parameter inference, which we plan to do with not just JWST observations, but also line intensity mapping experiments with COMAP and SKA in the future. And then what we are most interested in is to expand this parameter space in a real sense, and then we face a very tricky situation. That is that we need to run a lot of simulations, and then super resolution becomes necessary, because we don't just need high resolution simulations. You would say, okay, you want to run something Millennium TNG like? No, we do not want that. We want something even higher, because this is just one example from one of the papers, but this is something that has been shown again and again, that we have observations from JWST and other HST and other telescopes which give us galaxies in the UV luminosity function, and we have simulations which have the resolution to kind of resolve them, even with hydrodynamical simulations like Tizan. But the gray region is essentially talking about the dimmest galaxies, the smallest galaxies, which we expect to form when the first galaxies started forming, and we do not really sample them either with observations or with simulations. And what this means is that our simulations are essentially sampling from a prior of total galaxies, which is biased, and we are simply accepting that bias because it's matching with the observations that we have so far. But then you would say that, okay, you want to run really high resolution simulations, and you want to run lots of them because you want to vary parameters. How do you do that? That brings us to the project that the LOFA team has come up with, and that is called the Zoom and Enhance project. And eventually, we want to train MLGPR with that. Okay, I have 45 seconds to talk about Zoom and Enhance, but it's fine. And that is the part for the for simulations part. Let's go very quickly. The schematic, I don't need to talk to you about it, because even today, Tree also showed a similar schematic. But this is essentially what we want to do. We are basically trying to generate merger trees, but also positions of these halos. So we are taking halo positions, halo velocities, halo mass, scale factor, and something called a change variable, which basically tracks if a merger happened earlier or not. And we want to add random noise to each of these arrays independently. Of course, they are correlated, but we want to see if we can get away with keeping them independent and then just doing the super resolution. And the first phase is to just increase the density of these per time step. And the next phase is to essentially increase the number of time steps we get. So if you input a simulation from running from, say, Redshift 12 to 5, I want to have something that also gives me information from Redshift 20 to 12. And the benefit over analytic methods and GANs is mentioned here. I think I should stop now. And the benefit of training on halos is that we have less amount of data to deal with, and it's easy to generate halos. One of the ways is to just take all the different combinations of, say, for example, from dreams or something, and then for each of those initial conditions, just run simulations, and you have thousands and thousands of halos. But the limitation is that we don't track sub-halo information in this. And yeah, we have a bucket list of things we want to do, and I should end here.
I appreciate you staying on time. Great job. Okay, questions? Lucia?
Yeah.
Would you tell us a little bit more about this, the merger tree thing? And
I mean,
uses you imagined for it? Why are subhalos hard?
Yeah. So to be completely fair, it's something I've just started working on. I thought I would have more progress by the time of this meeting, but postdoc applications got in the way. But yeah, so the idea is essentially that we are trying to take merger tree information from a traditional simulation and then be very careful in the sense of introduce more branching first with this super resolution. So we would take information in an array and just try to increase the interpolate between the array essentially. But we are yet to test it to whether it works or not. What we did test was that using GANs was not the best idea because we're kind of getting similar results when we vary cosmologies, but we would want to see an impact of the cosmologies which was there in the traditional simulations. But yeah, we just want to introduce halos, have merger trees, so we have positions and merger trees, because then we can use that with any kind of semi-analytic model and then post-process with radiative transfer. Radiative transfer really cares about your positions, and that's something that we are not so, that's very tricky, and it has not been done that well in the past either.
Other questions?
I was wondering when you were varying the star formation efficiency in the polar simulations, is this to kind of reproduce the idea of free feedback-free starbursts that have been set to probably explain these massive galaxies and
pretty much. So what it in a very convoluted way, because semi-analytic models, what we are trying to do is there have been ideas about stochastic star formation leading to starbursts and things like that, leading to the kind of brightness that we see. So the idea of varying the star formation efficiency is something similar. And the reason we want to vary it is because changing the cosmological parameters changes how matter clusters. So you basically want to see how much of a starburst you need if your matter clusters more or less, essentially. So that's what it controls, yeah.
Okay, should we thank Anshuman again? Next we have Florian, Kéruzoré. Great, take it away.
Does this work? Can you hear me? Sounds good. Okay, hello everyone. Thank you for still being here. I'm Florian. I'm a postdoc at Oregon, so one of the people you've heard to referred to before as the dumb people with big computers. And today I'm very happy to be talking to you about Picasso, which, as you can see, is a very far-fetched acronym standing for Painting Intracluster Gas on Gravity-Only Simulations. Shout out to Daria. There you go. So the nice thing about giving my presentation at 4 p.m. on the last day of the conference is that I can blast through my introduction because you've heard all of this already. I don't have to convince you that clusters are very cool for cosmological data sets. And I don't have to convince you that to do cluster cosmology, we need simulations. Neither do I have to convince you, actually, that we can do that with two types of simulations, either gravity only, in which case we need post-processing techniques to emulate baryons, or hydro simulations. And what I want to talk to you about today is Picasso, which is a machine learning powered model that tries to do that. So painting gas on halos in gravity-only simulations with the goal to apply that to create data sets for cluster cosmology. That was fast. So this is the full workflow of the model. So that's quite a mouthful, but we can actually understand the Picasso model a lot better by by splitting it into two parts. And what you can see is that we are combining a parametric gas model with a machine learning trained model to predict the model parameters. So focusing on the bottom part here, the core of Picasso is an analytical gas model that is going to take as input for one given halo a distribution of gravitational potential, which can be a profile if you just have access to that, or a 3D grid, or the full particle information, and then give you as an output the thermodynamic properties of the intracluster gas estimated with the same sampling, so either a profile or a grid given, depending on what you have given to it. And all of that is conditioned on the fact that you have a vector of parameters for your parametric gas model with all of the components that are described here that I won't go into too much detail about. But the big thing about Picasso is that this vector of gas parameters is predicted using machine learning. And so the idea is that, again, for one given halo, you give a fully connected neural network an input, which is a vector of properties of the halo. So with the table that is listed here, you can see that you have different halo properties, such as mass concentration, different measurements of halo disturbance state and of morphology and of mass assembly history. And it predicts for you the best fitting set of model parameters. And so the idea behind Picasso is really to combine these two approaches of an analytical gas model and of machine learning so that we can have the interpretability of a physical model as well as the performance and the flexibility of machine learning. And so in order to make sure that our model makes good predictions that make sense, the part that is actionable is this fully connected neural network here. And to train it, we're going to be using pairs of matched simulations. So that is some of the simulations that Nick was talking about earlier, for which we have one set of initial conditions that has been evolved twice, once as a gravity-only simulation and once as a hydrodynamic simulation. Meaning that if I take the dark matter distribution in my gravity-only run, such as what you can see on the right here, and I look at the dark matter distribution in the hydro run at the same position, you can see that I find a very similar structure, which is the same halo. But the big thing being that because this is a hydro simulation, I also know the gas properties for this halo at this position. And essentially, Picasso is going to be trained to, given the input on the left, so the dark matter distribution in a gravity-only run, predict for us the properties of the gas from the hydro simulation for the matched halo. And so going back to the workflow, the way that we're going to do that training is by completely forward modeling the gas properties in the hydro simulation. So for one given halo, we're going to measure the properties of the halo as a vector and the potential distribution, completely forward model to make a prediction of gas density, pressure, and non-thermal pressure fraction. And then compare that with the target data, which is going to be the same properties for that same halo in the hydrodynamic run. And because all of Picasso is written in JAX, this loss function here is completely differentiable with respect to the parameters of the neural network, which makes it very easy to train it using gradient descent. And so the first model that we're going to train is what we call our baseline model, in which we are going to be using the full input data vector that I have presented to you before, so all of the properties of the dark matter halos. And we're going to be training to reproduce in the first-hand a non-radiative hydrodynamic simulation, so a simulation in which we have hydrodynamics for baryons, but we don't have any subgrid models. And you have the results of the training here. So I do the training on about 8,000 halos and save about 1,000 for a testing set. And for all of the halos in that testing set, once I have done the training, I compute predictions from Picasso, and I compute the ratio between these predictions and the truth from the hydro simulation. And I show you here the results of the ratios between these as a function of distance from the halo center. And if we focus in particular on the thermal pressure, which is what is most interesting to me because I'm a TSZ person, you can see that on average we have predictions from Picasso that are based at the percent level for Picasso, which is really nice, and a dispersion that is of order of 20%, which is comparable to what techniques like baryon pasting can achieve, which we already know has a very promising potential because it doesn't have a large impact on cosmology. So calibrating your cosmology analyses using baryon pasting maps instead of hydrodynamic simulation maps has a low impact on your cosmological constraints. Then we do a few other trainings of the model, especially focusing on removing some of the properties that go into the input vector, in case people want to use the model without having access to the full merger history of a halo, for example. So we design our compact model in which we just remove information related to the mass accretion history of the halo, and then our minimal model in which the only thing that you know about the model is mass and concentration. And you have the results shown here in orange and green. And long story short, not having access to the mass accretion history of the halo doesn't degrade your constraints by all that much. And even just having mass and concentration, you lose in precision of your predictions, but you are still able to make some pretty good quality predictions. Just a very quick performance assessment of Picasso. So what I did is I implemented my own implementation of baryon pasting. So in full disclosure, that is like completely CPU only and not done with a lot of like performance in mind. And I'm sure Erwin's or other people's implementations are a lot faster. But essentially, in predicting gas properties from the same geometry, so for the same halo on the same 3D grid of potential, we can see that Picasso gives us about 4 orders of magnitude speed up in predicting gas properties compared to baryon pasting, which is super promising, not only for mock data creation, but also for using it as a forward model, for example, for field level inference. And so I will leave you with my conclusions, saying that I hope I convinced you that Picasso is a pretty cool new model that leverages the advantages of analytical models and of machine learning. All of it is implemented in JAX, so it's like completely GPU accelerated and differentiable. The results are pretty promising in terms of reproducing properties from hydrodynamic simulations. And we can see that we can degrade the results a little bit, either when we remove access to some of the information that we give the neural network as input, or as I didn't have time to show here, if you try to reproduce properties from hydro simulations that do include subgrid models. Picasso is already publicly available. You can check it out on GitHub and pip install it. It's pretty easy, I think. Well, I should say I developed it. If it wasn't easy for me, it would be a problem. And you have full documentation that includes tutorials on how to use it. And so our next steps are going to be both retraining on the simulations that Nick was talking about earlier and exploiting it to create some synthetic data sets. And I will just leave you very quickly with these images where you can see that Picasso is not a completely spherical model. You have here some, for a few halos in our testing set, you have some TSZ images created for halos. So in the hydro run on the left and from Picasso trained and predicting from just the gravity-only matter distribution on the right. And you can see that we do reproduce the amplitude of the SZ effect, its shape, and even to some level, some substructure. And I will leave you with that. Thank you very much.
Awesome. Thanks, Florian. Great name for a baryon painting.
Thank you.
Questions? Chano?
Yes.
Just curious about what happened on the third row. So in the hydro, you can clearly see there's another like halos. I guess there's merging.
You mean for this one?
Yeah.
I swear to you, please attest that if you look on the screen here, you do see a little bit of it. I swear to you.
Yeah, we see it.
You can see
oh,
it.
you can see it a little bit here too, I guess. So it is not as strong. The TSZ effect in that substructure is not as strong, but if you look at the actual matter distribution, you can see that the subhalo in the gravity only is a little bit shifted too. So it's not as massive, which explains why you don't get exactly the same image, because you do have a little bit of differences between halos in gravity only and hydro.
I see. So you mean just the dark matter distribution is different?
Yes, correct.
Questions?
Last question. So when you were selecting the dark matter only to make the painting, I guess. So I mean, when you run the hydro simulation, you show also at the beginning, like the pseudostructure or the smarter structures are not necessarily going to be in the same position, and some of them are not going to be even there.
Yes.
So is this painting taking some sort of cutoff in structures that should not be formed because of feedback or whatever?
So in the training specifically, because what we are learning is really the mapping between potential and gas thermodynamics, we choose to train using only azimuthal profiles of gas thermodynamics and of potential. So that means that you smooth out these differences between gravity only and hydro halos a lot. But then once you have learned the mapping, you can apply it to just arbitrary potential distributions and presumably be able to reproduce the correct substructure associated to the gravity-only potential. Don't know if that's clear.
Yeah, just thinking like, there might be some bias in the numbers, smaller structures, because there will be structures that are not going to be found in the hydro simulation as opposed to the one that's just dark matter only and painting, even with the clouds, right?
Yes, that's true. That's true. And I think that's part of the scatter also that we see in the comparison between the predictions and the truth from the hydrosims. Yeah.
I think that's all the time we have for questions, but let's thank Florian again.
I don't know how. Okay.
Next, we have Michael Kovač.
Yeah, can you hear me in the back? Okay, good. Perfect. Okay, my name is Michael. I'm a PhD student at the University of Bonn. And today I'm going to talk how we can simulate the Zuňáv-Seldovich effect using magnification that was already presented 2 times today. Sorry about that. Also about the motivation, I think I can go quickly through that. As we all know, baryonic effects are one of the big systematics, and using hydrodynamical simulations brings problems with it. They're not only expensive, but also depending on what kind of subgrid model we use, they're also very different. Now, what we need is a fast and flexible model on one hand, and on the other hand, we need observations to constrain that model. So, as already mentioned, I'm going to present the baryonification model, but it's going to be a new version. It was first time presented in 2015 by Aurel Schneider and Romain Tessier, and this was further improved in 2019, and right now we're working on a rather new version of this model. Now, let me quickly wrap up how it works. So the idea is the same as for the old model. We take a dark matter-only simulation and semi-analytical profiles from gas, collisionless matter, and central galaxies, or stars in general. Then we go into the halos, and we shift those particles according to those profiles. So more specific, so the particles in the centers are pushed even more towards the center, which mimics the cooling, and the particles on the outside are pushed even further outside, which mimics the AGN feedback. You can see that very well also on this plot here, where we have an integrated mass profile of a halo, and the initial profiles are shown as a dashed line for the baryons and for the dark matter, and then the final profiles, so the analytical profiles, are showed in a solid line, and what we in the end do is really just move the particles from the initial profile to the final profile. Now, as I mentioned, the model is already kind of old, so what is new? So in the old model, we get the total matter distribution. In this new model, we get the individual matter distribution, so we get the density field from the gas, the dark matter, and the stars individually. This is one of the changes. We also changed the density profiles and also some back reaction models, but I won't go into detail for that. This is in preparation and should be published pretty soon. Now, having the model, we of course also have to validate that that model works. We did that using the high-resolution fiducial flamingo simulation as an example. We did that also with other flamingo suits and also TNG, but here I'm showing the fiducial flamingo. So on the top, you see density profiles from the gas multiplied with the radius squared. On the bottom, you see the pressure profile, which was calculated using hydrostatic equilibrium and the non-thermal part. And the columns show different mass spins. Now let's have a closer look to the central mass spin. In black, you see the density and pressure profiles from the flamingo simulation with its 1 sigma regime. And in red, you can see our best fit coming from the baryonification. And as you can see, we are well within the 1 sigma. So we are able to reproduce profiles from hydrodynamical simulations. Now, having the model validated, we can go to the second point, namely the observations. Here I use two probes. One of them are the CMB secondaries, so namely the Zuňáv-Seldovich effect, which is an inverse Compton scattering from the CMB photons either on the bulk velocity, which is then the kinetic Zuňáv-Seldovich effect, or on the high energy electrons, which is the thermal Zuňáv-Seldovich effect. This is one probe that I use. The other probe that I'm using are X-ray measurements. More precisely, I'm using gas fraction measurements within a specific radius. Now let's jump directly to the results. So what I did is jointly fitting KSC measurements and gas fraction measurements using our beneficiation code. Here on the left, data points, I think you're all very familiar with them, are the ACT measurements, stacked ACT measurements from the CMAS BOSS sample, and the solid lines are showing our best fit with the 1 sigma regime. And as you can see, we can reproduce very well the measurements. Now on the right side, you see the gas fraction profile for different masses. And also here, you see we can reproduce those high mass regions very well, except for that rather low mass region point. This might be explained due to a selection bias, so that we only see galaxy groups with a rather high gas fractions. The star indicates at what mass our CMAS BOSS sample would be. Now, having this done, we can again compare to hydrodynamical simulations. We did this as well using Flamingo. So in green, you have the fiducial Flamingo gas fraction profile, so the same I showed before. And in red, you have the strong feedback Flamingo profile. Now, as you can see, for the higher masses, the fiducial Flamingo agrees very well. But as soon as we go to groups or even very low masses, the fiducial Flamingo tends to overshoot the gas fractions. For the lower masses, the strong feedback Flamingo tends to agree a bit better. Now, since both probes depend on the gas profile, we can also have a look at the gas profile. More specifically at the gas profile which we need to reproduce the KSC profile. This is what you see here on the left. So the blue line shows the gas profile which is needed to reproduce the KSC measurements, and the red line here shows the gas profile which was directly measured out from the Flamingo simulation from the strong feedback model at redshift 0.55, from where also we have the measurements. As you can see, the agreement is well within 1 sigma, but what you also can see, the KSC tends even to go to a stronger feedback. So you can see that we have less gas in the center and more on the outskirts. Now, as a peek, how a power spectrum could look like, I have that plot here as well. So the power spectrum that we will get with the parameters that we get from the barnification is the blue one. And as you can see, it is even stronger than the strong feedback power spectrum from Flamingo. This indeed helps a bit to reduce the SA tension, but I didn't make any further tests on that. But that's what I'm planning to do in the future. Yes, with that, I can leave you with my conclusions. So we have a new model which we can also use in future to do simulation-based inference with multiple probes. Thank you very much.
Michael. Questions for Michael? Yeah.
What's the mass you get, and what's the x-axis?
You mean here?
Yeah.
So the x-axis is M500.
Yeah. No, I mean the data. What's the mass calibration for those X-ray samples?
Okay. Here I used as well also mass bias because the calculated mass was done by using the hydrostatic equation. So I had to include the mass bias, but this only shifts the mass points a bit to the right from your side. But yeah, I didn't show the results. I have actually new results with the new eROSITA data. They look way better, but I didn't have time to prepare them very well, so I showed some old results I did.
See ya.
In the next slide, this one, what does the fiducial Flamingo look like for this plot?
The fiducial Flamingo is actually above the end of the scale. It is really pretty high in the inner part, and then has a really steep fall down. You can also see that very well when you look at the gas fractions here. So this is the mass we're looking at. This is the gas fraction needed for the KSC within a radius of R500C, and the fiducial would need a gas fraction here. So we really need way more gas in the inside.
Any other quick questions? Yeah, Paco?
This new baryonification model, now you can split in dark matter, stars, and gas. So, I mean, you show that you are able to reproduce this very well. Will you be able to also reproduce things like the stellar mass function? Or given this, already you have a tight constraint too?
We actually didn't think about doing that, but it might be worth to check that as well. The goal actually right now is really use gas fractions, KSC, hopefully also TSC, and in the end also FRBs to give constraints to the model so that we have probes on all mass scales, which is what we tend to do.
Let's thank Michael again. Thank you. Next, we have Supranta, right? Supranta Boruah. Take it away.
Okay. Hello, everyone. I'm Supranta. I'm a postdoc at Penn, and I work on field level inference for analyzing weak lensing data. And I'm going to talk about some of the new work that we're doing to use generative models, generative machine learning models in our pipeline. And by field level inference, what I specifically mean here is the Bayesian approach to doing field level inference, where what you do is you try to jointly infer the cosmological parameters and the maps from the noisy data. And broadly, when you want to do this approach, you can broadly divide up the probability model into two parts, where in the first part, what you need to model is the probability of the map given some cosmological model, which is basically the prior that you want to have in your model. And then we also we had this discussion about how we want to have a good field level model to describe the full observation, which will give you the likelihood that you want to use in your field level inference. So in this talk today, I'm just going to be talking about this green box here, where we want to improve the prior that we use in our field level inference pipeline. So this generative model that you need to use to model the prior, so there have been different field level pipelines that people have described. And so far, I think there are two broad strategies that people have used for in field level inference pipelines. So the first is to model the final density field from some initial conditions where the prior is invoked on the initial conditions because it's simple to describe. It's effectively Gaussian. Or we also heard approaches from Bhuv and Kunhao where you can describe the full field level prior using some sort of analytical models. And if you put these classes of models in the space of speed and accuracy, we see something like this, right? And usually we have some sort of trade-off between speed and accuracy where the approximate methods like log normal models fall on the upper left part of this plot where the model is fast but not necessarily that accurate. But then the n-body simulations are accurate but they're super slow. And what I'm going to be talking about is how we can leverage these analytical approaches to go to the upper right part of this plot where we can create many simulations fast. Of course, there are methods, or there are projects currently on just using analytical methods and improving them so that we can get to that part of the parameter space. And for weak lensing, the analytical model that works very well to describe the full field is the log normal model. Oops, sorry. And so this is a plot taken from a paper from a few years back, which shows how the convergence field look like compared to Gaussian and log-normal fits. And log-normal model pretty much describes the convergence field very accurately at the scales where what we care about for doing cosmology. So we put out a code called Karma where we used log-normal priors to infer dark matter maps from DES year 3 data. And here I'm showing some of our results. So on this plot here is the map that we get from Karma. And the other plots are the methods that were used by the DES collaborations. So what you see is that in the Karma map, you see that we end up resolving much smaller structures than compared to, say, the Wiener filter approach, which is probably like the most apples-to-apples comparison with Karma in some sense. But that's just a visual trick, and like Humanizer famously deceived very easily. But if you try to compare different statistics, for example, like the power spectrum of these, the 2-point functions of these maps, you see that the 2-point functions of the Karma map shown in these blue lines actually traces the DES, the 2-point function that you measure from DES data almost exactly right, which is something that the current mass mapping method can't do. So that's a good thing to have, which basically means that the Karma maps have similar statistical properties to the real maps that we expect from the data, whereas the other methods do not. And I should say that while creating these mass maps, at our first go, we just fixed our cosmological parameters. But we did have a forecast on how much improvement do we expect from doing a field-level approach, field-level inference approach for inferring cosmology. And what we find is that for something like inferring the dark energy equation of state, for something like LSST data, we get much stronger constraint with field-based inference compared to traditional power spectrum approaches. However, if you just do a lambda CDM approach, you don't necessarily gain that much. And I think this is a point that has been studied by many groups by now. Okay, so the log normal works well, but of course, it's not that great. So if you look closely at the maps that you infer, you do see some small biases. And if you actually look at the significance of these biases, for stage 3 surveys, these biases are actually not that huge. So if you look at the chi-square statistics of some of the different non-Gaussian statistics, they're virtually indistinguishable for DES year 3. But if you go to the stage 4 surveys, your log normal prior is not going to be enough. You can clearly see that the log normal model actually differs quite a bit from simulation methods. So what we propose is that the log normal model already does pretty well. So why don't we use some sort of machine learning approach, some sort of generative machine learning model to input some log normal model and get the full simulation quality maps out of it. And that's what we did. And the approach that we take is GAN, like the generative adversarial network. And I know that GANs are not very fashionable these days, but I want to convince you that you can still get a lot out of these GANs. And precisely how we do this is usually when you take a GAN-like approach, the latent space that you use is some random latent space from some normal distribution. You go to creating a full map. But that's not what you necessarily need to do. For example, we can make the latent space quite interpretable. We can input log normal maps and have that as our latent space, and then use the GAN to just learn small tweaks on these maps to create simulation quality map. And when we do that, it actually does really well. And not just that, we can do this training with very small networks, order 1,000 parameters. And we only need a few full sky maps to get this full thing done. The GAN we build is on full curve sky maps. And sorry, I think I'm out of time, so I'll just skip these things, except I'll say that, the GAN is quite explainable. You can see that what it does is it takes some big blob in the log normal maps and make it a much more compact peak. And you can see what the action of the neural network is in this approach. I will skip this, except to say that the GAN, like you can compare the non-Gaussian statistics, and they look pretty good. Okay, I'll skip this. Okay, I'm quite out of time, so I'll just end it here.
Thank you very much.
Okay.
Questions? I have one to start off.
Sure.
When you did the forecasting for the cosmological constraints,
Yeah.
you said you did the reconstruction with fixed cosmology, and then you forecasted it. How exactly did you do that?
No. So I should be clear. No, this is a different approach where we fix the cosmology.
Oh, okay.
Here, we are doing a forecast. In our forecast, we are varying both cosmology and the field consistently.
Okay.
Yeah.
So the typical question that you get with GANs is like, how do you know that you don't have mode collapse?
Right. So first of all, I think like the reason why mode collapse is much less of a problem here is that so if you have some mode collapse here, then that's in the process of same log normal model should correspond to two different simulation maps, basically. And it's entirely possible. We did some tests in terms of trying to train different GANs and look at cross correlations between different maps. And it seems like that cross correlation is much smaller than the cross correlation, or the difference in the cross correlation is much smaller than what you get from the log normal and the simulation. So that's one test we did. But yeah, of course, you can get other tests, I guess.
Okay, I think that's all the time we have for questions. But thank you very much, Supranta.
Okay, sure. Thank you.
Okay. We have next Mauro Rigo. Cool. You all set?
All right. Can you hear me? Okay. So bear with me for 10 more minutes. This is the last talk. I'm Mauro. I'm a PhD student at CCA in Italy. And today I'll be talking about Gerald, which is a code/approach to produce high-resolution dark matter and baryonic maps starting from approximate and body simulations. So this is a very, very standard introductory slide, so I'm just going to quickly go through it. You've seen it a million times. I'm just going to say that Gerald falls in the category of algorithms that starts from approximate and body simulations, so dark matter only, and populate them with baryons through some machine learning technique. In this specific case, the approach is a little bit more physical, and it was introduced in 2021 by Diane Selyak with the name of Lagrangian deep learning. You've actually already seen this during the conference, but I'm still gonna describe it a little bit. I hope not all of you know it, so this is still gonna be kind of useful. Anyway, so let's say we start from an approximate and body simulation, and we know that these simulations generally give good dark matter distributions at large scales, but usually over the small scales, they lose a little bit of power. So the idea is to fix for this mismatch by modeling, in an effective way, by modeling an additional displacement for the dark matter particles. So practically, we start from dark matter particle positions from an approximate and body simulation, here indicated with X, and we model this additional displacement S as the gradient of a potential that depends on the dark matter distribution, in this case, the overdensity, and some additional parameters theta, and this is where the machine learning comes in. These parameters theta are optimized by essentially minimizing the distance between the map that is produced, this delta model, after displacing the particles, and some reference simulation, this delta target, which could come from a full body simulation instead, which has the correct, quote-unquote, dark matter distribution. This is cool, but the thing is that this is not necessarily limited only to dark matter, because at least over the large scales, baryons trace the motion of dark matter. And so dark matter particles could sort of be reinterpreted as baryons, which have a good distribution over the large scales, but not so good over the small scales, where all the complicated baryonic physics happens. So this is the same setting that we had at the beginning, and so we can use exactly this approach in the same way. Although in this case, for baryons, there are processes that cannot just be modeled by moving the particles around. So to give you an example, for stellar mass, we have star formation. This is more of a sort of thresholding process in an approximate way. So it cannot just be modeled by moving the particles around. And so the idea is to apply a final transformation to this delta model, and you'll see this more in detail in a second. Just to give you a visual interpretation of what happens, we start from dark matter particle positions from an approximate n-body simulation. We displace them through some displacement layers that you saw before, and then we train the parameters of the displacement layers by producing a map with CIC and making this map match with some reference map coming from, for instance, from a full n-body simulation. Then the idea for baryons is that we can start from these improved dark matter particle positions, apply additional displacement layers parameterized with different parameters, produce again a map with CIC, apply a final transformation that you'll see in a second to produce a stellar mass map, and then we train all the parameters of these things here by making the output map match with the reference simulation with the loss that you just saw before. This is more of a technical slide. This is the expression of the effective potential for dark matter and stellar mass. You can see it's just a Green's function and a source term. And the Green's functions are written in Fourier space because this allows to straightforwardly implement rotational and translational symmetries. But what I wanted to focus on is this expression here at the bottom. This is the transformation that I was mentioning before for stellar mass that should sort of approximately model the effect of star formation with this value here. The things I highlighted in this weird yellow are the free parameters of the model. So you can see that there are not many, and they have sort of a physical meaning, which is kind of neat. So let me focus now on something which is new and a little bit more of interest for me, which is neutral hydrogen. Neutral hydrogen is very complicated, as you may know, especially at low redshift. Its distribution is it has a huge dynamic range, and it's very heavily affected by the presence of stars, for instance, with feedback and ionization and so on and so forth. So I thought of at least introducing the effect of stars by introducing a pre-trained stellar mass map with the same produced with the same pipeline that you just saw before in the model itself in two places. One as an additional term in the potential, which is the exact same expression as before, but in this case it depends on the stellar mass distribution, and also an additional term in the final transformation. And the term in the potential should sort of approximately model effects such as feedback, and instead the expression in the transformation, it should approximately model the effect of ionization. So this is the idea. Now let me go back to the pipeline that we saw before for stellar mass. This is where we left off. Now, when we have this map, the stellar map here trained, we use it, and we integrate it in the pipeline with additional displacement layers, again producing a map with CIC, and again with the transformation, but the ones that you saw in the previous slide instead, to produce a neutral hydrogen map. And then once again, we train all the free parameters of these things by making the output map match with the reference one through the loss that you saw some slides ago. This is the idea. Let me show you some of the main results. These are power spectra for dark matter, stellar mass, and neutral hydrogen. You see three groups of lines in every plot. You see a blue group, an orange group, and a green group. They're associated to redshift 0, 2, and 5. And in each group, you see a solid line. That's the power spectrum associated to the reference maps, the ones coming from full hydro simulations. And then you can see some dashed lines, which are the power spectra associated to the maps produced by Gerald. In the case of dark matter, you can also see a dotted line. That's the power spectrum associated to the approximate n-body simulation, which you can see loses some power over the small scales. And you can see that in every case, Gerald is capable of producing maps which have a very good agreement in the power spectra with respect to the reference simulations, even at very nonlinear scales. And this is only with at most about 30 parameters. So let me now give you some perspectives for future work that we plan to do. The code is written in JAX and C++. It is very fast once it's trained, which takes approximately 4 hours. It just takes some seconds to generate even very big maps. And so the idea would be to use it to just generate mock catalogs maybe, but also, as we've seen many times during the conference, as a forward model for field-level inference, or also to generate big data sets for training algorithms that learn optimal summaries, such as we've seen many, but like information maximizing neural networks is an example. So that's it. If you have any questions, feel free to ask, and otherwise, let's just go for a drink. No, there's a discussion. So.
Awesome. Thanks, Mauro. Any questions? You have one, Paco? Go for it.
So you have this parametric function to do the mapping.
Yes.
So I was wondering, so if you relax, for instance, this and you put like a neural network that is like much more flexible, do you expect to increase the accuracy of your...
I would expect maybe, yes, to increase it. So the thing is, it could be introduced in many different places, because the idea would be to still keep, let's go back a little bit, the expression sort of like this. Maybe one could introduce a neural network in the expression of the Green's function, because the idea is to still keep the Green's function written in Fourier space for translational and rotational symmetries. But this would include, so the kind of neat part of this is that it has sort of a physical interpretation, because those are kind of filters for, let's say, low frequency and high frequency. And also at the same time, it has very few parameters, and so it's also kind of easy to train. So that would be the idea. But I kind of tried a little bit, not investigated it too much, but yeah, that's an idea.
Questions?
You said this. What were you using for your reference?
Sorry?
What were you using for your reference simulations?
I'm using, I don't know if I've written it. I think I may have, but I did not mention it for sure. Yes, it's Sherwood Relics simulations. I don't know if you know them. They're simulations that are supposed to model accurately the IGM, because initially our idea was to mostly focus on the Lyman alpha forest. And so, yeah, these simulations are supposed, they don't implement self-shielding, for instance, so they mostly focus on the IGM, and because we initially wanted to mostly focus on the IGM in the first place.
Okay, so, I mean, so a follow-up question. Is there a version of those simulations that's dark matter only that you can...
No, actually. I don't think so, or maybe yes. Is there? Okay, yeah, there is.
Okay,
So I haven't...
I'm just kind of wondering how the mapping goes from dark matter to stellar mass, since the baryons also move the dark matter around. If you're training it on a simulation that already has the dark matter moved around by the baryons,
so
that messes up the mapping or not?
Yeah, basically right now we use as a reference for the training of dark matter itself a map that comes from a full hydro itself, actually. So it has already the dark matter moved by baryons. Yeah.
Okay.
I think that's all the time we have for questions. Thanks, Mauro.
Thank you.
Finally, we have our last discussion of the evening. Would you guys like to come get set up? Yeah. Nice.
Should we just talk into...
Yeah. Can we use this one as well?
Thank you.
Both on.
All right.
Great.
So hi everyone. I'm Jonathan.
And I'm Stephanie.
And we have a dance prepared. No, not actually. So since we are the last official event, first I think a huge thank you to the organizers for an amazing week.
Yeah. Okay. All right. So, without further ado, sorry, late voters. We went with what was winning by the time we made the polls. So, so we had way more great questions than we can discuss because I think everyone's tired. So, I think without further ado, let's jump to the polls. So, wait, actually, everybody get out your phone, do the little QR code. We're going to do live polls.
Yes.
Get ready.
And while you're doing that, we should explain. So we had all the questions. You guys voted on them, and then we basically went down the list, and the first 6 or 7 of them we translated into multiple choice questions, which you will see in order in a second. The wording might be slightly different, so in case you're confused, we had to retype everything and make it sensible for a multiple choice question, but hopefully we captured the sense of the question.
Okay, great. Can we go to the first poll question, please? Okay. So, can we emulate the analysis pipeline well enough to go directly to observables? Yes. Somebody says yes. That's great. Right. You can make your vote, and then you can raise your hand and tell us what you mean. Do I have a count? Oh, okay, I do have a count. So we have 38 votes. That's pretty good. It's still like, we're still ticking up.
All right, 10 more seconds.
Hurry. Vote, vote, go. Hurry up. Panic, and vote. Okay. All right, lock it down. Okay, this is the final vote. Wow. People are pretty optimistic.
I guess not a lot of weak lensing people in the community. So this question was partly, so this is my question, full disclosure. This was partly motivated by some talks we had today, including Chen Hao's talk. So, you can do a beautiful emulation or forward model of, say, a kappa map, but that's not actually what you see when you point your telescope up in the sky. And there's a lot of steps to get from a very messy set of pixels on a CCD to a kappa map. And so those last steps, should that be part of an emulation pipeline? Should it not? Do we understand it well enough to emulate it and trust that whatever comes out of our black box is relevant? Anyway, that's what I was trying to get at. So apparently we're split on this. Do people have thoughts on this? Yeah, Tom.
I voted yes, because I didn't fully understand what you mean stop at theory. And so that was the confusing part, because a number of things, that forward modeling that we have in mind, I mean, that's the part we're trying to learn. So in a way, we'd never stop at theory. Right? The way I think about it is, you've got your theory, you make your model, you try to explain it as best as you can, and then you keep refining until it works. That's what threw me off at the question of why would I stop at theory.
Okay. Well, now that you have the explanation, are you changing your answer? We should stop at theory?
I didn't fully understand it, but that's my shortcoming, I think. I mean, there's some cool things one could do about making those maps. I mean, the particular example you used, I am always surprised by that this is how it's done. That you make a map and a noise map, because you start at a catalog level. So the actual statistics you do, and it involves nearest neighbors. Now you could do maps where you just go out from random points and ask, find your 100 nearest galaxies and look at their mean. And so that would be an adaptive map in space. It wouldn't have a fixed aperture. And the noise, the statistical noise, is the same Poisson noise for each of the measurements. I mean, that's just one sort of random idea, but those are the type of things you could do and circumvent some of the particular examples you mentioned, I think, where you introduce nuisance parameters like scales, noise, thresholds, that I think are actually unnecessary. I believe, I'm not an expert in this, but it surprises me that that's the choices you make when you first go to maps, when you have such beautiful catalog data to begin with.
Anybody willing to fight for maps, or are we all going with Tom and going to do catalogs from now on? Yeah.
Like when you say like you forward model the kilo level, are you also including forward model the photometric redshift, or you?
If I understand you correctly, right? You segment first, sort of define what are galaxies. Then you look at their colors in a specific aperture. So, and from that you determine a photometric redshift.
Yeah.
Then you get a shape measurement.
Yeah.
So now you have a position with a shape and a photometric redshift.
Okay.
Right. That's your catalog.
Okay, so your catalog is already a photometric redshift for individual objects.
I'd love to go crazy. Let's talk about images and see more directly. But I'm just saying, now that you have that catalog, I'm surprised to go to image, to make new maps next, because this is totally as an outsider. I'm just saying, if you just now look at regular points or random points and ask, okay, how large is a region that contains 100 galaxies, and take the average shape in that region, I think that would be a nice thing. The noise would be the same in every measurement, and you wouldn't have gone to an actual, introduced another nuisance scale. I mean, we picked the K now, the number of neighbors that you picked. Yeah, but we're a little bit in the weeds. I'm just saying, there's so many choices you can make of how you change your pipeline, and the ones you pick, you can really go through metrics where try not to introduce any nuisance parameters if you can avoid them. That I think would help in not having to stop somewhere.
Any last thoughts?
Okay. Let's go to the next one. I think we did a word cloud. I'm not sure if that was a good idea.
All right. Well, what mock observables would we want from future hydrosims?
Yeah, you can put in a few. Correct ones. We had a lot of TSZ talks for TSC to be so tiny. What's going on over there? Okay, there we go. That's better. Wow.
Take 10 more seconds.
Okay.
Hey, Fergie.
All right. Okay, good. 3 people are typing. No, now 5. Stop typing. Yeah, 3. Okay, let's go. 6. All right. Okay. Wow, well, people still really like Lyman Alpha Forest.
Does someone want to defend one of the bolder, bigger choices? Make your case. Really?
Sure, I would like to know colors, because, I mean, it would be nice to be able to say things about star formation rate, anything that's going on in the galaxy, past the basics. Also, some of these are not observables, I feel like.
Well, you want to call something out other than Siobhan?
Well, like, I would say star formation rate isn't an observable. Or, like, things like that. I mean, I guess it depends on what you're classifying as an observable, but I would feel like you have to do some kind of thing to go from what you would see to what that actually interpreting what that means in that case.
Yeah.
So, I mean, the question doesn't specify, but you could interpret this as what do we want to be able to model from hydrosims, but you could also flip it around and say, if we want to figure out which hydrosim is right, what are the most useful observables? So as someone who personally is interested in doing weak lensing, I care about that second question. Can someone tell me which of these I should care about for figuring out which hydrosim to trust?
I don't think you should trust any hydrosim. Not really. I mean, we can learn things from them, but we're never going to get one totally right, right?
Yeah. Right. I mean, I think you're stuck with everything in that case. Okay. Do any of the tiny ones? Does anybody want to fight for a tiny one? IFU, morphology. We had some good morphology talks. No? All right, let's keep rolling. Okay. Oh, sorry.
I'm not going to defend anything, but I guess so. We're a whack dark matter. I guess maybe they're advocating for more non-CDM sims. Is that? Also, I like the choice of whack, maybe.
Right. I mean, that isn't an observable, so that's a fair, yeah. It's a fair question. Does anybody want to explain what they meant by whack dark matter? Or you can pretend that your friend did it and you know what they meant. No?
Yeah, I wrote whack dark matter because I'm really tired of reading theory papers where they say how like a power spectrum changes and they end it at that. But I would like to see like simulations where you kind of can have a whole host of like this is actually confirmed, or bet more. I have more confidence when like a simulation will tell me, oh, this is what's going to change, and how things are going to look forward, versus just here's a power spectrum, go build a nice telescope to find it.
Okay. Interesting. Does anybody want to fight for power spectrum as a great thing to look for and should be what we use to determine the appropriate whack dark matter model? No? I mean, a lot of people showed power spectrums in the past 4 days, so somebody has to like them.
Power spectrum doesn't need to be defended. It's doing fine.
Okay. All right. So, okay, I think let's go to the next one.
Yeah.
What do you say? Okay, yeah, I think this was one of our top voted ones. So, what should we focus on emulating? Full sims, summary statistics, intermediate theory quantities, like power spectra. How are we doing on votes? Pretty good. Mm-hmm.
So, if you're a spectroscopic person, maybe, but if you're a lenser, no, that's the middle part of your calculation. Can't actually see it.
Okay.
And really, even if you're a spectroscopic person, there's other stuff that you still have to add on afterwards.
Okay. All right. Well, it looks like full sims is winning. Does anybody want to trash full sim emulations?
Well, if I can, I think this question is missing the time frame. Because ultimately, of course, we want to get it. But the question on what time scale? A year? 10 years? Ultimately?
Okay, so eventually full sims when everyone has argon computing.
Eventually,
and then,
yeah.
but for now.
There's no question about eventually, that's right.
Okay.
Whether it's my lifetime, though.
I kind of want to advocate for full simulations just because, like, the interesting thing about it is it allows us to break up the problem into different stages. Like, if we, ran everything and then only emulated the summary statistics, then all the assumptions we bake into the simulation, like, get baked into the emulator, and you can't change any of them unless you have, like, a million knobs to tune in your neural network or something. But the nice thing I think about emulating full simulations is, you can emulate the dark matter part. You could, in theory, then emulate the galaxy part. Then you could, in theory, emulate the dust part. Then you could, in theory, emulate the photometry part. And then you can, pick and choose kind of all the different knobs you tune and test every combination of all of those, which I think is the most exciting thing.
Yeah.
I want to know what we actually learn from emulating. Maybe it's useful. I agree it's useful.
It's useful.
Okay?
Yeah.
We do big surveys. We want a good model, right? And we want a survey strategy and all this, right? So I agree it's useful to planning and all this stuff, right? But what do we really actually learn from emulating? Let's say we have a good emulator model. Are we learning something really physically meaningful from that?
I don't think so. I think it just speeds up our existing analyses. I mean, like the perfect world is one in which you had infinite compute power, like they have at Argonne apparently, and like you could run like every simulation to full resolution every single time, and then you just find the right simulation which looks exactly like our universe. But unfortunately, we can't do that.
Right.
So I think it's just an acceleration of existing analysis.
Right.
Yeah.
So by definition, the word emulate means we learn nothing from that. Because it's imitating, right?
Yeah.
The true answer. So why are we doing this if we don't learn anything?
Possible to do it the classical way, I think.
Okay. Danielle looks like but Tom had his hand up for a while.
We just wanted to add a yes and in the sense that, yeah, simulation will be great, but for a lot of the cosmology things that we're talking about, I think we want the full forward model. I mean, including masks, selection effects, the whole thing that the thing we're producing is something we cannot distinguish anymore from real data. Right? That's the thing we want to get to, and that's what we want to emulate, because once we have that, then there's no question about how we talk about our errors, how we talk about our theory errors, and also how we compare it will be very straightforward, because it's essentially the same object that we're dealing with, and we won't be worrying about which summary statistics you use, because you just say use all of them, and all of them need to match. But so I think, yeah, that's sort of a yes and.
Danielle, you had your hand up, and then Florence.
Yeah, I mean, maybe going back to the emulation, I guess, so we've seen examples where constructing an emulator that can predict, I don't know, galaxy properties as a function of like the 20 or 30 parameters that we have. So it's been useful to just interpret, or just as an efficient interpolator that can allow us to like visualize how different feedback parameters are affecting the properties. And so in terms of interpreting and trying to understand physically what's the impact of each parameter, it's been useful to manage the like huge mess of data that we often have. So maybe in that sense, as a tool to be able to analyze things maybe a little easier if you trust that it works and is reproducing the simulated data accurately.
To add to what Tom was saying, but it kind of relates to what Danielle is saying right now. So it just if you have the full simulation, and then in your data there's a signal, right? You find something, you want to know where it came from, like what in the data is causing that signal. If you only have the capability to simulate your summary statistics, then you don't know what's weird really in the data. Like you lose a lot of interpretability. Like if you have access to something that can simulate the whole thing, then you can trace back, okay, like that's weird in my summary statistics that I can get from those, but then this comes back from this and this and this. Like these are the simulations that are consistent with the data that I have, and that's where this specific signal comes from. So it becomes a lot more interpretable, I think. So yeah, maybe you don't really learn anything from a simulation in the sense that you only get the physics that you put back in, but then you can actually learn to interpret whatever you find in your data. So it could be very powerful to have access to emulators of the full.
And to add, I think we have in many cases already data where with the absence of a forward model, you can't explain to people of what you find in your data. And then if you can't explain it to a broader range of audience, then it's not going to be so useful if people don't believe the result.
Minor to add. We're like sort of building off of speed, but also sensitivity. I mean, if you have some underlying simulation which is not differentiable, and we've heard a few examples this week about differentiables, these days it's pretty easily done to cast a surrogate that is differentiable via neural network. So then suddenly that sensitivity analysis is really easily achievable, but also very fast, right? So that could be example, assuming your emulator isn't biased, which is of course a valid concern, but that could be an example where suddenly that is something that you could do that you couldn't do with your original simulation.
Good point. Oh, yeah.
So emulators may not directly learn something from it, but if you have an emulator which says that, okay, as if we have these parameters in an emulator, it matches with this observable, then that then if you try to see what in your actual traditional simulation matches with what the emulator is getting, then that is an effective way to basically narrow down your parameter space. So even if you don't learn the physics directly, the emulator could give you a sense of direction when you do not know what part of parameter space to focus on, based on basically because we cannot run all traditional simulations. So, but we can know which ones to run and compare with observations if we have a sense of directions from emulators. So maybe that helps. That depends on the emulators themselves, but we'll see.
Yeah, I'm going to take my prerogative and just say one thing. So I don't know. I mean, given that there seems to be so many degeneracies with your ability to match, it makes me nervous to try to narrow down the parameter space that I really want to focus on, just because I managed to get like really close one time. And so I think, I don't know, that feels clever and dangerous at the same time to me. But maybe like definitely a way forward and to try to use emulators. Chris?
Yeah, I'm just going to be grumpy for a second. So I'm just a little confused at this characterization of emulators as just reproducing your training data. I think the whole, the selling point of emulators is that they enable us to explore new regions or new statistics and new regions of observable space that we can't achieve with the fiducial simulations we have. Like the canonical version of this is that we train an emulator on, say, some high-resolution simulations and then apply them to something low-resolution to increase, say, the volume, right? Or we train them on sort of dust radius transfer simulations and then apply them to much larger volumes so that we can accelerate these processes. So, maybe we don't learn anything, but they enable us to do really cool stuff, right? And that's the real selling point.
Paco, did you want to have a finishing comment? I know you had your hand up a while ago.
Yes, I mean, I don't know. I don't know what is the exact definition of emulating, but it's not the best hydro simulation that we have right now. Just an emulation of the real universe, like a very bad emulation.
A very bad emulation?
Well,
it is bad.
And still we learn a lot from it, right? I mean, from these things. So.
That's a fair point. Okay, should we end on the most depressing note and jump all the way to our last question?
I think let's try one more and then end at the very depressing.
Okay. All right. So, can we go to the next one? I think this is sort of connected to some comments that people were making, so this is good. Okay. How well are we able to connect small high-res sims to the huge N-body or PM sims needed for cosmological analysis? You solved it? That's right. So for those of you who don't get my bad joke, TSZ, you can stand it in for whatever your favorite observable is that you don't think needs small high-res sims. So maybe TSZ is a bad example of that, but there you go. See, how is mine too? I feel like subgrid physics is a big problem. Yeah. Thanks. Yeah, I really want to hear who solved it. I was focusing really hard this whole week, and so.
I'm surprised that one of the options isn't this is computationally incredibly difficult, keep dreaming. But is that what you meant in until we understand implementing? Or is that a different thought?
I mean, it probably is like both things baked in.
Yeah.
Right. I mean, I guess if we could do what we currently are implementing as subgrid physics from, having individual stars and giant simulations, then okay, that would solve it too. Or we just need to figure out, how to not use Bondi-Hoyle approximations for our black holes or torque accretion. It's good too. That's great. I mean, that's right, obviously. I know that. Okay. Does anybody have anything they want to comment on? Is there an observable where we don't actually need to make this connection? Do we have one where we don't have to worry too much about the small scales?
FNL.
Yeah. Okay. Well,
on the FNL, hard to disagree.
For things like CMB lensing, I don't think we need very high resolution, right? Or I might be wrong. For things like this, yeah.
Okay, so that's where we should really focus our energy until we figure out subgrid physics.
This was my question, and I feel like we're missing the spirit of it, which was like...
Sorry.
No, it's okay. And I think like Chris kind of spoke to it this morning, right? This like the problem of like, we know these problems and we can simulate them decently well at small scales, but it's just like accessing the volumes is very hard. So I think I wanted to ask like, as an overarching picture, like we saw how zooms do it really well, but is that the only place? So cosmological analysis can also be like broader, like, if you're doing clustering analyses of emission line galaxies, something like that.
Yeah, maybe I guess we've seen quite a few talks about baryonification models and advances in that direction. So maybe we could rephrase as, is baryonification enough for a lot of the cosmology, and can we just do that and forget about understanding the physics on smaller scales, or is there some gain that we can hope for to, I don't know, get better measurements or still be able to improve understand information on the smaller scales if we manage to understand the physics better?
But I thought that baryonification moves my particles based on what I think baryonic physics is going to do to my particles, which is like subgrid. No? So
I guess maybe without necessarily having to understand why is that they're moving, or I mean, I guess that could be at different scales, but anyway.
Yeah. Do you want a closing statement, and then we gotta wrap up?
No, I think towards what you were saying, I think with baryonification it's a bit as the second answer. As long as we care about the TSZ, we are good because and then whenever we want to train something more fancy, we need anyways these small scale simulations so we can inform our models. So I think for the very large scales, baryonification can be very good and flexible, but then if we want to dig deeper, we need more, I think.
So maybe should we go to the very last question as our farewell to everyone?
Done a really high. It got highly ranked. a lot of people, a lot of you voted for it. So, yeah. So what about the environmental impact?
And then everyone can go catch their plane home.
Yeah, exactly. That's right. Shoot. Who talked? Argon. The Argon. Yeah. Oh, somebody is against moving to bigger and bigger sims. Okay. Yeah. Right. I don't know. For me, before COVID, I was all gung-ho on virtual meetings, and now I really like flying places. So, okay, does anyone have a real comment on this? Or is this like, now I need a drink?
So I have a comment about the meetings, that it was a few years ago, so I don't know how it looks like now, but probably not a huge change. I have seen someone calculated the environmental impact for astronomers specifically. I don't know if that was worldwide, but meetings weren't the biggest factor, even with flying around, so it was still supercomputers.
It was.
So we shouldn't feel too guilty about coming here.
Ah, good. Great. That's right. Okay.
Yeah, my view is slightly different on this. So I think we use the Durham supercomputer, and every 3 months they provide us an email with okay, this is how much you used in terms of energy, and they, well, as they're British, they also say this is how much cups of tea you could have heated with it. But they also say how much flights it is, and I think the biggest Flamingo run, that was equivalent to 40 people taking a transatlantic flight. So then the computing, yeah, is not where we should look.
Well, but if we need to run flamingos with all of our different whack dark matter models and all of our different subgrid models and, try to get a
that's not
hypercube.
Going to happen anytime soon anyways.
Yeah, okay. So it's, whoa. Okay. I don't know. Lucy, I saw your hand first.
I just feel like I'm not going to feel bad for like doing science when people are mining Bitcoin and like, rest in peace, Jim, but like burning so many CPU hours to just like trade on the high-speed trading market. So at least we're trying to understand the universe and in pushing forward science and statistics.
Fair point. Did you have?
Yeah, since Nick isn't here from the FES, I just wanted to mention that for a lot of these supercomputing clusters, the main energy drain is just keeping them cooled. And so regardless of what you're doing, that cost is going to go away. So at Argonne, Nick was actually helping them a lot by actually making sure while they were cooling things down, it was actually getting science out rather than just standing still there. This is an active conversation he had with the Frontier folks. He mentioned this before. I'm just bringing these up for folks who aren't as used to using the Argonne supercomputer. Okay. This is the case for a lot of places where the actual energy cost isn't just because you ran a single simulation. It's an ongoing energy cost from just the computer existing.
Right. Yes. Good point.
Modern data centers are not like this anymore. Different data centers that use fresh air much more.
Yeah, there are. We could like require better cooling systems for our computers that would perhaps mitigate some of these issues. Yeah.
I think we saw some beautiful examples today of people actually being clever about picking very specific zooms and then reproducing the full statistics. That's really much less computing. And these big boxes, they really don't make sense. I mean, what's the point of having 100 million modes? Your statistics, you're only trying to get 1% error bar, right? So with many of these big boxes, you're really much better off in breaking it up into smaller things. And this is true specifically when you only do the power spectrum, like you're not even looking much at other quantities. I think it's really useful to take that incentive to think about the environment, to strategize of how to organize your computing better, because it really is an inefficient way, and it's total overkill. The error bars are way too small. And your systematic error bar is much bigger. So it really is not a sensible thing to keep using so many modes on the small unresolved scales.
Yeah. I feel like somebody had a picture of the northern cap and the southern cap earlier in the week, and I think they'd fight you, but I don't know that they're here. Okay. Are we gonna?
We used emulators for that. So.
Oh, okay. Well, there you go. All right, perfect. Saving the environment. Okay, we'll go. I haven't heard anybody in the back corner, and then we're closing it out for real.
Great. And maybe ending on a good note, which is, yeah, this might just be justifying the fact that we're not mining Bitcoin, because I haven't done the actual calculations, but I think the way of creating like a human civilization that is compatible with not burning down the planet is scientific advancement. And so like it's probably true for some of us more than others about what results could be used for that. But honestly, a lot of these things, especially if we can loop them in more with people like hydro sims, how does that relate to studying the atmosphere of the ocean? Then like the work we can do, does it help more than it hurts still? I don't know. Haven't done the calculations, but like it's contributing to something. We're making the world a better place.
Okay, I love that. We're shutting it down. That's it. We're done. Thanks again, everybody.
Sorry, so just before we leave, I just want to thank everyone for coming, everyone for presenting such high quality work. I mean, with the SOC, when we started looking at the abstracts, we felt like it was going to be good, but I think we were really pleasantly surprised. Everything was so high quality, the posters, the discussions. So thanks, everyone. Thanks for the Zoom participants. And I hope some of them are still outside and can hear us. So thank you for the coordinators team led by Christina. Thank you, the AV team and the wonderful catering team that kept us going.
And also, we already thanked the SOC, but Shai really did 90% of the work for this, so let's thank Shai.